This is part 3 of Microchip's cryptography primer. In this part, we will discuss hashing and its use in symmetric cryptography. Hash is a fundamental building block of cryptography. You are probably already familiar with hash. A CRC, a cyclic redundancy character, is a hash, although it's not strong enough or robust enough for cryptography. A crypto hash uses a strong, irreversible mathematical transform. The characteristics of a strong crypto hash are similar to a CRC. It's easy to compute the digest. You just feed in the data, and at the end you get a fingerprint of that data. It's infeasible to regenerate the original message. Anyone who knows a CRC realizes they cannot recreate the file that the CRC was derived from. With a crypto hash, it's also infeasible to modify a message without changing the digest. This is untrue regarding a CRC. You can change the message and wind up with the same CRC. So that's a big difference between a CRC kind of hash and a security hash. It's also infeasible to find two different messages with the same digest. The output of a hash is called a message digest, and it is of a fixed length. And sometimes it's referred to as a fingerprint of the file. And if you put in a 1 kilobyte file into a crypto hash, you wind up getting a fixed output. In the case of a SHA-256, you would get a 32-byte message digest. And if you put in a 1 megabyte file, you'd still get a 32-byte message digest. A 1 gigabyte file, again, 32-byte message digest. A hash can also be used to authenticate a message. When a hash is used to authenticate, the name changes. It's called a MAC, a message authentication code. Sometimes you'll see this as MIC, message integrity code, or a tag. I have no idea why it's called a tag, and if any of you know, please leave a message. The reason I show this slide is there is a frustrating tendency in the cryptographic community to use multiple terms for exactly the same thing. You'll see this over and over again. If you're new to cryptography and you're reading about something and it looks like they're talking about something you already know, it's pretty safe to just assume that it's the same thing. You'll probably be more right than you are wrong. So now let's use hash in symmetric key cryptography. Other terms for symmetric key cryptography are secret key, shared key, single key, parent key, and there are others, but you get the drift. Again, we're talking about multiple names for exactly the same thing. Symmetric cryptography uses identical keys for both encryption and decryption. If you can imagine, Alice goes to a hardware store, buys a lockbox with two identical keys. She then gives Bob one of the keys, and now they can use that lockbox to transfer secrets back and forth to each other and not worry about people, a man in the middle, reading their secrets. The way Alice and Bob exchange keys is very important. In this case, Alice and Bob know and trust each other. Alice can give Bob a copy of her secret key, and Bob is assured it's genuine and trusted because of his knowledge and trust in Alice. But Alice needs to give Bob the key in relative security. In other words, an adversary can't have the chance of getting any information about that key. They can't take a picture of it or get any information whatsoever about the key. It's critically important that the key stays secret. This is the simplest form of key exchange between Bob and Alice, or between two entities when they know and they trust each other. This is the simplest form. We will get into a more complex form where Bob and Alice do not know each other and they have to somehow establish trust in the asymmetric section of this presentation. Again, I can't stress this enough. The keys must remain secret and secure. The vulnerability of this system is in the confidentiality of the key. Are there other copies of the key that Alice didn't know about? Was the change secure? Was an adversary able to glean some sort of information about the key? Does Bob value the key the same as Alice? This is a very important point. Maybe Alice thinks this key is incredibly important, but Bob not so much. Is there someone Alice and Bob trusted with the key, but they shouldn't have? Secret key can be extremely secure, but great care must be going into to protecting the key. Secret keys are on a need-to-know basis, and the number of copies should be aggressively managed. One of the best examples of when you should use secret key versus public key, which we haven't actually gone over yet, is when you have an ecosystem which is all yours. Your network does not have to interoperate with any other vendor's products. So essentially, there is no Bob. It's only Alice. It's Alice's. Every node in the network belongs to Alice, and Alice maintains security of that key and does not have to trust anyone else with it. Here's how hash is used in symmetric authentication. Alice wants to authenticate a connection with Bob. Bob and Alice know each other and have copies of the identical secret key. So Alice starts off with her shared key with Bob, and Bob, of course, has the shared key as well. She creates a random challenge and sends it to Bob. Bob then takes that random challenge and runs it through a crypto hash like a SHA-256 with the shared key. Alice does the same thing on her side. Bob takes the resulting digest, sends it back to Alice, and then Alice does a binary compare on what she calculated. And if it compares, then yes, she knows she's talking to Bob. Note, I didn't say this connection between Alice and Bob was secure in any way. There actually could be thousands, if not millions, of people watching that transmission. But what did they see? They saw a random number go to Bob, and they saw the digest come back. And the digest to them looks like a random number. That digest only has value to Alice because Alice and Bob are the only two people on the planet who share that key. Now let's use this in a real-world example. Authenticating a battery, for example. First, we'll talk about how the computer and battery are provisioned. Provisioned means set up so that they can communicate with each other and talk with each other. Let's talk about how these things are provisioned in the factory. The OEM creates a parent key. This comes from headquarters and is, of course, protected. There is a manufacturing line. There is the batteries that we're going to create on the manufacturing line, and there is the notebook computers that we will be creating as well. We take the parent key and put it into the hardware security module that's on the manufacturing line. The hardware security module is similar to a crypto element or a TPM. This is simply a hardware enforced, persistent, secure environment in which keys and primitives, crypto primitives like authentication, integrity check, and so forth are protected. Once the manufacturing line starts to create batteries, it will ask for the unique serial number which is in every crypto element. It will then hash that unique serial number with the parent key. This will result in a unique derived key for that battery. The manufacturing line will then inject that unique derived key back into the battery. Now, that unique derived key will be useless unless the notebook computer is somehow able to recreate it. So, the notebook computer is given the parent key. This parent key is protected inside the notebook computer by the Trusted Platform module. Let's imagine a customer with our notebook computer goes out and buys a new battery, and they bring it back to the house and slide that battery into the notebook. The first thing the notebook will do is ask for the unique serial number so it can recreate that unique derived key. Once it recreates that unique derived key, it will then generate a random challenge to the battery. This battery will then hash that random challenge with the derived key, creating a digest. The notebook on its side will do exactly the same thing. It will take that random number, hash it with the derived key, and create an identical digest. Then it will compare the two digests, and if they match, it knows that this battery is genuine. Okay, so that covered identity authentication. We authenticated that it was Bob. We authenticated that it was a genuine battery. Now let's talk about message authentication. Symmetric message authentication. Bob wants authentication. A message came from Alice, and Alice and Bob know and trust each other and share the same key. So Alice and Bob both start off in the same situation as before. They have a shared key between them, or copies of the same key, I should say. Alice generates a message and sends it to Bob. Bob stores it on the side. He's not going to use it right away. He's not sure it's genuine. He runs the message through a crypto hash along with the shared key. He just takes the message, he appends the key to it, and then runs it through the function. Alice does exactly the same thing on her side. Then Alice sends the result, the digest of her hash, which is now called a message authentication code because we're authenticating a message, and sends this to Bob. Bob then takes his digest result, compares it to Alice's digest result, and says yes or no, that if this is a genuine message from Alice. Now, although this slide implies that Alice just did two separate transmissions, that's really not the case. In reality, what Alice would do is she would create the message, she would then create the MAC, she would append the MAC to the message, send the whole thing to Bob in one transmission. Bob would receive that message, strip off the MAC, store the message to the side because he doesn't know it's genuine yet. He would hash that message and then compare the MAC Alice appended and the MAC he just created and say yes or no, this is a message from Alice. Now we'll talk about using symmetric cryptography to generate session keys. What are session keys? Session keys are used with a cipher to obfuscate messages. To encrypt, we use a cipher, which needs a session key or keys. A cipher is a math function which uses a unique key to uniquely obfuscate input, clear text, turning it into unreadable output, ciphertext. There are many types of ciphers. There's AES, DES, triple DES, Cha-Cha-20 is becoming popular. Ciphers also have modes of operation. You may have heard of AES-CBC or AES-GCM. Covering ciphers in detail is a completely different presentation. We have one of those, so please look that up if you're interested. A critical mass of ciphertext using the same key presents vulnerabilities. Therefore, temporary keys are used and frequently changed to thwart these vulnerabilities. Hence the term session keys. A session could be any length of time. A session could be every message transmission, or you could have a session open for a full day and all the transmissions of that day would use the same key, or maybe a full week. Really, this is a decision up to you. It depends on how much ciphertext you're creating. If you have a small IoT device, which is just putting out very low amounts of data, then you can have a session open for a longer time. If you're putting out a lot of data, then you might want to consider having a session be every single message. A single transmission could even consist of multiple sessions. The financial and military communities tend to change the session key every 100 milliseconds. So they're changing the session keys within a transmission. Let's see how symmetric cryptography is used to create these session keys. So Alice wants to send Bob a secret message. So they're going to need a session key. Alice and Bob have previously shared an identical secret key, of course. So they start off with the same things as before. They both have the same identical key. Alice creates a random challenge. She sends it to Bob. This is looking familiar, right? Bob and Alice both take that random challenge and hash it with the shared key. Again, they just append the shared key onto the random challenge and send it through the math function. The output now is called a derived key, and this doesn't go anywhere. They keep it close and safe, each one of them. Then they use this as the input to a cipher, and Alice can now take plain text and turn it into ciphertext, and Bob can take that ciphertext and turn it back into plain text. Thanks for watching Microchip Channels, and I hope you learned more about embedded security.